first video, I explained the basics of the atomic structure, in other words, the electronic structure of the atom. So today I'm going to explain how to write the electron configuration. The electron configuration is the way how electrons in different atoms are distributed in different orbitals around the nucleus. Before we write the electron configuration of atoms, we must know there are three principles which govern the electronic configuration. In other words, we write electron configurations of atoms following three principles. Those three principles are Aufbau principle, in other words, the building up principle. The next one, Hund's rule. The next principle is Pauli exclusion principle. The principle presented by Pauli, that is called Pauli's exclusion principle. So far we have understood that electrons in atoms are actually, they occupy atomic orbitals. That means electrons are arranged in main energy levels. Those energy levels are further divided to sub-energy levels. A sub-energy level is a collection of one or more atomic orbitals. That part I explained from the previous video. And one important thing is, when you consider atomic orbitals which belong to a particular sub-energy level, all the atomic orbitals which belong to that particular sub-energy level have the same energy. That is, they are degenerate orbitals. They have the same energy. For hydrogen atom, the atomic orbitals which belong to a particular main energy level, they all have the same energy. For example, first energy level you have s orbitals. Second energy level we know s and p orbitals. That means two sub-energy levels, s sub-energy level and p sub-energy level. Third main energy level, three sub-levels s, p and d. So there are s orbitals, 3 p orbitals, 5 d orbitals. For hydrogen atom, only one electron. The orbital energy of the hydrogen atom is determined by that particular main energy level. Only by the main energy level, because only one electron is there. That means, for example, in the third main energy level of hydrogen, you have s, p and d orbitals. They all have the same energy. That is for the hydrogen atom. But when it comes to atoms with more than one electron, there are atomic orbitals which are present in a particular main energy level. They have different energies. In other words, the sub-energy levels of a given main energy level have different energies. So we must first understand how the energy of these sub-energy levels vary when you move further from the nucleus. Move further from the nucleus. Now, to understand that one easily, I will first give you a particular method from which you can obtain the variation of the energies of these sub-energy levels and atomic orbitals very easily. When you look at this diagram, in the left hand side, you can see from this diagram, you can see in this diagram, I have first written the main energy level and the particular sub-energy level or sub-energy levels in that main energy level. That first main energy level, you have S1S. second main energy level S and P. So 2S, 2P. Third main energy level S, P and D. So 3S, 3P, 3D. Fourth main energy level 4S, 4P, 4D, 4F, like that. Then I have drawn these parallel arrows and connected in this order to get the increasing order of the energies of these sub-energy levels and atomic orbitals. Just below this diagram you can see I have written the variation of the energies of these sub-energy levels. So there you have 1s, 2s, 2p, 3s, 3p. After that you can see even though we expect 3d, it is 4s. Now that variation you can simply obtain using this diagram. For this variation there are different reasons. Normally in a given main energy level, when you consider the sub-energy levels S, P, D, F, like that, the energy increases in that order. That means third main energy level, energy of 3P sublevel greater than 3S sublevel. Energy of 3D sublevel is greater than 3P sublevel. But sometimes you can see that for S level, that energy is less than 3D level. So that is due to the penetration of the different orbitals with respect to the nucleus. So all these complex things we are not discussing in the A Level syllabus. What you are supposed to know is the variation of the energies of these sub-energy levels. So that Aufbau principle or the building up principle states that electrons are added to an atom starting from the sub-energy level having the lowest or the minimum energy. Electrons are added beginning from the sub-energy level with the minimum energy. Then electrons are added in the increasing order of the energies of these sub-energy levels. That is what is given by the building up principle. So according to that, you can see that the order in which electrons are added, I can write like this: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, like this. That means first electrons are added to the s orbital, then 2s orbital, then 2p, 3s, 3p, 4s, like that. This is the order in which electrons are added to the atom. When we represent an orbital, now atomic orbitals have different shapes. In the last part of that part I will explain with the section quantum numbers. Now, when we represent an atomic orbital, simply, even though they have different shapes, for example, s orbitals are spherical in shape, p orbitals, there are two lobes we call dumbbell in shape. D orbitals, actually 5d orbitals are there, 4 of them have 4 lobes there, and the other d orbital is quite different from the shape. It has like dumbbell shape and around that something like a donut. So 5d orbitals are more complex than 3p orbitals, and f orbitals are even more complex, their shapes. But simply an orbital we represent using a square like this, or even if you use a circle, no problem. The second principle you must understand when you write the electron configurations is the Hund's rule. So I explained the building up principle. According to that, when electrons are added to an atom, they will first be added to the orbital or sublevel with the lowest energy. After that, the next lowest energy, like that, electrons will be added in the increasing order of the energies of these sub-energy levels. When electrons are added to orbitals of a given sublevel, as I explained, degenerate orbitals, where the energies are identical, these electrons are added one at a time, resulting maximum number of unpaired orbitals with the same spin. Maximum number of unpaired orbitals with the same spin. We'll try to understand what is meant by this. Now, as I explained, an atomic orbital simply we represent like this. In an atomic orbital, in the previous video also I explained that the maximum number of electrons that can be present is 2. When there are 2 electrons in an atomic orbital, we represent like this with 2 opposite half-headed arrows. If you represent the atomic orbital using a circle, you can write like this, no problem. Sometimes full-headed arrows are also used, but it's better if you use half-headed arrows. When there is 1 electron in an orbital, one half-headed arrow, it is drawn upwards, only 1 electron. Now just think of these atomic orbitals as in the previous diagram. The energies of these atomic orbitals, I showed that they increase like this, 1s, 2s, then 2p, 3s, so 1s, 2s, 2p, 3s, like this. This axis is energy. So when electrons are added, according to the building up principle, electrons are added to this atom starting from the lowest energy orbital. So if you consider an atom with say 6 electrons, say carbon, atomic number 6. First electron will be added to this 1s. Then 1s can accommodate for another electron, second electron. Third electron goes to 2s. Fourth one also into 2s. Then fifth electron to 2p. Now 2p level you can see 3 orbitals with the same energy. When electrons are added to the orbitals of the equal energy, they are added one at a time, so that maximum number of unpaired orbitals, unpaired means an orbital with only 1 electron, paired means an orbital with 2 electrons. So when electrons are added to orbitals of the same sub-energy level, they are added resulting maximum number of unpaired orbitals with the same spin. After that, they may get paired depending on the number of electrons. Now for carbon, first electron, second one, 3, 4, 5, and sixth one, it does not come to this orbital, it goes to the next orbital of the same energy. Next orbital of the same energy. Let's consider another atom, say an atom like sodium, 11 electrons. I will erase this. So first electron 1s, second electron again 1s, so 2 electrons, then 3, 4. Then here, this is the order in which electrons are filled. 5, 6, 7. After gaining the maximum number of unpaired orbitals, then they get paired. When they get paired, always the spins of these two electrons are opposite. We draw these two electrons, or we represent those two electrons so that spins are opposite. I will explain this in detail under Pauli's exclusion principle. But before that, I want you to understand the electron configuration, how to write the configuration. Then 1, 2, 3, 4, 5, 6, 7, then 8, 9, 10. After that, there. When we write the electronic structure or electron arrangement of an atom, we write like this. Now in this sodium atom, for example, you can see first main energy level is sub-energy level, 2 electrons, 1s2. Second main energy level is sub-energy level, 2 electrons, 2s2. Second main energy level, p sub-energy level, 6 electrons, 2p6. Third main energy level is sub-energy level, 1 electron. Now this number represents number of the main energy level. Number of the main energy level. In other words, we call the principal quantum number. This is the type of the sub-energy level. Sub-energy level or in other words, type of the orbital. And this superscript number, that is the number of electrons in the particular sub-energy. You can see in this atom, first main energy level is sub-energy level 2 electrons, second main energy level is level 2, second main energy level p sub-energy level 6 electrons, third main energy level is sub-energy level 1 electron. So this is how we write the electron configuration of ground state atoms. Ground state means the state where the electrons are present in the minimum possible energy states. That means the electrons with the minimum possible energies. That is the ground state of the atom. In an atom where all electrons have the minimum energy. That is called the ground state. From the previous video, you learned that when moving further from the nucleus, energies of these energy levels increase. Energy gap decreases, but energy increases. Therefore, when electrons are more closer to the nucleus, the energy will be less. Right, now you can see I have written the electron configurations of first 13 elements: hydrogen, uh, helium, lithium, beryllium. You can understand this. And here, say carbon, 1s2, 2s2. When you consider 2p level, 2 electrons in 2 orbitals, same spin. If you draw this one in a different way, for example, if you write like this, that is wrong. To represent all both together, that is wrong. Right? So once you understand the Pauli's exclusion principle, you will get familiarized with this configuration more. And when it comes to nitrogen, again you can see 1s2, 2s2, 2p3. These 3 electrons are added to 3 orbitals with the same spin. And oxygen, 1s2, 2s2, 2p4, that means 1, 2, 3. The 4th electron comes to one of these p orbitals in which it gets paired. Then fluorine, 1s2. We stop from this because that orbital can accommodate only 2 electrons. Then next electron goes to the 2s. 2 electrons could be there. Then 2p, 5 electrons could be there. When it comes to neon, 1s2, 2s2, then 2p6. Now this p sublevel is full. There are 6 electrons. Therefore in sodium, 1s2, 2s2, 2p6, 3s1. When you consider sodium, 1s2, 2s2, 2p6. 1, 2, 3, 4, 5, 6, then 3s. 1s2, 2s2, 2p6, 3s. Magnesium, 1s2, 2s2, 2p6, 3s2. Aluminium, 1s2, 2s2, 2p6, 3s2, 3p1, because 30 electrons. So this is the way how we write these electron configurations of ground state atoms. Right. We'll write the configurations of few elements where the atomic number is quite high. You always need to remember this variation. That means you can easily draw the diagram and deduce that one. You are not supposed to memorize everything. At any given point, you can just draw the diagram and obtain that variation. But later, once you write these configurations through the syllabus a few times, then you actually get familiarized with this. Right. This is the variation. 1s, 2s, 2p, 3s, 3p. After that, we know that 4s, 3d, 4p, 5s, 4d, like this. We'll write the electron configuration of an element, say titanium, atomic number 22. First, I will draw the orbitals. 1s, then 2s, 2p, 1, 2, 3, 3s, 3p, 3d is there, but before that 4s is filled. Here I will draw the 3d orbitals, there are 5. 1, 2, 3, 4, 5. Then 4s. So first electron 1s, and second one also 1s, then 2s, 2p, 2p6, then 3s2, 3p6. After that, electrons go to 4s level, 4s2. Now we can see 4 plus 6, 10, 12, 18, 20. The next two electrons come to 3d. Again, it follows that Hund's rule. So when you write the configuration, 1s2, 2s2, 2p6, 3s2, 3p6. After that, actually 4s is filled, but when we write the sublevels or orbitals of the same main energy level together. So you can write 3d2, 4s2. Even if you write this by changing, one cannot say that is incorrect. That is also accepted. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. One of these methods could be followed. So that is how we write the electron configuration of titanium. Now, according to this method, you can write the configurations of all these elements in the syllabus. Mainly expected to know the configurations of first 36 elements, but it's better if you can write the electron configurations of first 54 elements. There are few exceptions. Apart from that, all the other elements you can write the configurations using that building up principle, Hund's rule, and Pauli's exclusion principle. Actually, Pauli's exclusion principle states that when two electrons occupy a particular atomic orbital, their spins are always opposite. That is one way of expressing the Pauli's exclusion principle. The other way of expressing the Pauli's exclusion principle, uh, the way we normally define that is, no two electrons in an atom can have the same set of quantum numbers. That means no two electrons in an atom can have identical values for all four quantum numbers. You will understand this after the lesson quantum numbers.